Okay, so the talk will be on current-induced switching of an antiferromagnet, of the magnetic order in an antiferromagnet by really reversing the antiferromagnetic order. So you reverse the Néel vector and to detect electrically this state, which is believed to be actually equivalent. Because if you think about an antiferromagnet, when you just make a transition operation of one of the atomic places, you actually back in the reverse state. So macroscopically, such a state is identical, and still there is a way to detect it, and this I would like to talk about. Because I think, well, first of all, I tell you where I am. So here we have the world, and you have India, this huge subcontinent India, where you're probably somewhere located here. I am on the, well, half rotated of this globe, sitting in Germany somewhere, about here. Well, if you zoom it up, this town is called Regensburg. A very nice old town, 2,500 years old, founded by the Romans, when the Romans actually were here. And it is famous for being, first of all, a very old and pretty medieval town, and having actually the oldest stone bridge here. So what you see from the top is actually this stone bridge, which is the oldest stone bridge, maybe not in the world, but at least in Europe. Yeah. So that's why it's famous. It belongs also to World Heritage. Well, so, but I don't want to talk about this Regensburg. I want to talk about antiferromagnets. And the question I actually ask you, do you believe this could be indeed something useful for applications, for spintronics application, such then, for example, for hard disk drives, so like the ferromagnetic systems, they're obviously useful, like for mass data storage, hard disk drive or magnetic random access memory, right? And this question I try to answer today. Well, first of all, on the first glance, they seem to be useful because they join two very similar properties of ferromagnets. They have a magnetic order as ferromagnets, which is in a sense non-volatile because this order is based on the atomic magnetic moment, or on the spin of the electrons, if you want. And it's not charge-based. That's why it's also relatively robust against, for example, high energetic radiation. But it's even more interesting than metals, ferromagnetic systems, which are mostly metals. Antiferromagnets, it's actually quite a huge material system family. You can have insulators, antiferromagnetic insulators. Most of the antiferromagnets are actually insulators. Because of the magnetic structure, they can be even topological insulators. You have semiconductors, semi-metals, and also metals. Well, something which might be interesting and important, they don't, if they are compensated antiferromagnets, they don't generate a magnetic net moment. So they don't have the problem to generate stray fields, which may interact or cross-links to other magnetic structures. So they're also then insensitive to relatively small magnetic fields. This might be also a merit. And recently, people figured out that certain antiferromagnetic orders, they can be even such that you have a spin polarized band structure. So you like ferromagnets, they might be spin polarized, whereas this spin polarized band structure is coupled to the magnetic orders. This new type of antiferromagnets, which belongs to this class, are the so-called altermagnets, or also non-collinear antiferromagnets. They can have a spin polarized band structure, despite they have no net moment, which is also of very high interest. And maybe the most important feature is that the dynamics of antiferromagnets can be extremely fast. So typically, it's 3 orders of magnitude faster than ferromagnets, which are in ferromagnets typically on the gigahertz regime. Antiferromagnets, their dynamics is in terahertz regime. So on the transition between electronics and light. And of course, this makes them perhaps very interesting for application. However, the fact that they don't show a net moment is maybe not only a merit, but could be also a problem, because how you want to detect the magnetic state. Well, you may think about those states are different when you can zoom in and you can really look into the individual spins. But if you look to a macroscopic state, those two states seem to be identical, right? Well, there is an effect which can be used to distinguish at least orthogonal antiferromagnetic states. And this is a very old effect, known since about 170 years, the so-called anisotropic magnetoresistance effect. This effect was discovered by Lord Kelvin, as I said, about 170 years ago. And the origin is in principle a scattering of electrons, of itinerant electrons, on magnetic orbitals via spin-orbit interaction, which makes the scattering probability different depending on the magnetization orientation. Well, and this effect, despite it's usually not very big, was first used indeed for application as a read sensor by IBM in hard disk drives. This was the first read sensor about 30 years ago. This was indeed introduced and made a big change. Before they had only inductive read sensors, and the growth rate with respect to the areal density of those hard disk drives were changing from 30% to 60%. So quite a huge impact, despite the effect is usually small. The problem is this effect cannot really distinguish reverse states. So it's even with time reversal. And as you can see here, if you rotate the magnetization with respect to a current direction that you may define in your structure, it will follow typically this cosine square theta dependency, right? Like in permalloy, these are measured data from permalloy, and you see the effect is only 2%, so it's small. But as you can also see, there is a difference between the resistance if the magnetization is parallel to the current, or if the magnetization is perpendicular to the current. Well, if you consider both cases, in both cases, the electric field and the applied current are parallel. However, if you rotate, for example, the magnetization by 45 degrees, you will get a transverse signal. Your electric field is not anymore parallel to the current, and you'll be able to detect a so-called transverse AMR, which is also known as the planar Hall effect. However, it follows the same symmetry as above. Why it should be different? It just changed this angle by 45 degrees. Right. So this is very well known for more than 170 years. But it was first used to actually identify an antiferromagnet which you can manipulate by electrical current. And this antiferromagnet, well, you can use a probe current here in such a cross-type structure. And if you have the way to switch by some means, and this is actually the coupling between the spin and the orbital degree of freedom of electrons, the orientation, the antiferromagnetic orientation of such a system, in a way that you can do it by 45 degrees with respect to your probe current, you can indeed distinguish those two states if they are, say, in this horizontal alignment or in this orthogonal alignment here. Yeah. However, you cannot distinguish reverse states. They are unfortunately identical. How you can switch this magnetization? Here you use indeed this effect of coupling between orbital and spin angular momentum, and it is known in principle in a non-magnetic system as Edelstein effect. So if you have a system with a broken inversion symmetry, then you have effectively an electric field which translates in the rest frame of your electrons into a magnetic field, and the electron spin starts to process around or to aligns to it. And now you have here a system, this copper manganese arsenide, for example, is an antiferromagnet, where you have a locally broken inversion symmetry in such a way that your magnetic moments here for one sublattice, they are having copper atoms on top, and they have the arsenic atoms below. And therefore, the inversion symmetry around them is broken, and therefore they feel this spin polarized electrons. And if you send them in the proper direction, you may be able to rotate the magnetization of those manganese atoms. And the other sublattice, that's just opposite. You see the copper below and you see the arsenic above. Here, this inversion symmetry is just opposite, but still broken. And here you generate the opposite polarization of electronic polarization. And you might be also manipulate there in a way that this effective field, which interacts with your antiferromagnetic order, is staggered. So it changes from atomic site to atomic site. And therefore, it acts actually like a Zeeman field in a ferromagnet, here like a staggered Zeeman field to an antiferromagnet. And indeed, if you now apply short electrical pulses in this copper manganese arsenide, you can see that our readout signal, which we measure transverse AMR, changes for pulse by pulse by pulse. If you change it the opposite direction, it reduces, and so on and so on. It's not just a switching between two states, it's actually a multi-domain switching. And the origin of this is believed that this copper manganese arsenide can have a biaxial anisotropy, and therefore you have many small domains which then switch individually at certain current pulses, and you get such a kind of counter. Those counters are actually quite useful elements, because you can use them. For example, if you compare them how our brain works, we have synapses, which in principle learn in a way that they change their weight of, if you want, the resistance of letting electric signals through. And if you take those antiferromagnetic elements as a kind of artificial neurons, you can think about the artificial neural network that you can create out of this. So that's why those systems gained a lot of interest also for application. And the most interesting is that because of this very fast dynamics, you can even use polarized terahertz laser pulses and switch, depending on the polarization, if it's vertical or if it's horizontal, the orientation of the linear vector by 90 degrees. At least those measurements seem to suggest this kind of multi-domain switching. But what you also see, so for example, here you apply pulses in these gray areas, and then you apply pulses of the opposite polarization in the other gray areas, and the resistance either increases or the resistance decreases, this transverse resistance. But between, it looks like that. So what I wanted to say is that those orthogonal switching is not stable. So in time, you actually decay. And within a few minutes, the state information gets lost. The origin of this is not really understood. It may be because these two states are not really equivalent or whatever. But I don't want to go too much to this, because what I want to show you is that we actually aiming now to understand the reversal of 180-degree reversal of antiferromagnets, and also to detect it. And also to do it not only on a local way, but you do it actually for global state. And how you can do it? You cannot use the anisotropic magnetic resistance, at least not a linear response. Well, there is an effect, a transport effect, which changes sign when you reverse the magnetization. Typically, it's the so-called anomalous Hall effect. And this anomalous Hall effect is also present in some antiferromagnets, in so-called non-collinear Kagome antiferromagnets. There is a finite anomalous Hall effect, and you can indeed distinguish the reverse states when you switch the orientation of all the spins shown in this triangular spin arrangement. So this has been shown. But what about collinear antiferromagnets, like what we are looking to? So anomalous Hall effect, in principle, is present when you have a system where the time reversal is broken. Indeed, we have such a system, copper manganese arsenide, for example, taking this as our antiferromagnetic system. You have two sublattices, and as I said, you can distinguish those two sublattices, so sublattice A and B. You use a time reversal, you switch the magnetic moment orientation. And because here you have the copper below and here you have the copper above, you can principally distinguish those two states. Yeah. But if you do another symmetry operation. In this case, you use the inversion symmetry. So if you look there, the inversion symmetry actually switches you sublattice A to sublattice B back. This means your system, copper manganese arsenide, has actually a combined PET symmetry. So if you apply the time reversal symmetry operation and the parity symmetry operation, you are back in the original system. And because of this, right, if you think about your anomalous Hall effect, which is odd under time reversal, but it should be then obeying the PET symmetry in this, this crystal. On the other hand, the space inversion flips the sign of both the electric field and the current, whereas the time reversal symmetry flips only the sign of the current. And therefore, both equations are valid. And this means this anomalous Hall effect is indeed not existing in such a system by symmetry. Well, let's look to higher order magnetoresistance, actually to a second order response. And indeed, as one can figure out in this publication from Joao Godinho, you can find it, that in antiferromagnets, which have a broken T symmetry, but also a combined PT symmetry, this second order coefficient might be present, is allowed, at least by symmetry. And interestingly, most of the antiferromagnetic point groups, which have a broken T symmetry, also have a PT symmetry. So this is very good because we will have a lot of material systems which show this property. So let's start with the most simple antiferromagnet with PT symmetry. And this is just a synthetic antiferromagnet where we have two ferromagnetic layers, yeah, which are antiferromagnetically coupled over this iridium layer here. And on top of it, they have platinum on both sides. So this has a PT symmetry. And if we now apply, this material has an out-of-plane anisotropy, and if you apply a magnetic field along the EZ axis, you can, if the field is strong enough, break the antiferromagnetic coupling and you get in a parallel state. And then our anomalous Hall effect measurement indeed can distinguish the two states where it's the both layers are forced to be parallel to a strong magnetic field. However, the anomalous Hall effect can't distinguish the antiferromagnetic states. The same kind of GMR, if you think about giant magnetoresistance effect, right? You have two layers, you have somehow an intermediate layer and another layer. Also there, you can, of course, distinguish the state where the magnetization is forced to be parallel with the state which is then anti-parallel, but you don't know which anti-parallel state. So also here, you have no difference in it. Well, so one thing you can see here, our synthetic antiferromagnet is not perfect. You see a small hysteresis, and this hysteresis tells you actually that one of the layers switches before the other layer switches. So one is a master, and the other is a slave, is following because of the other. And this allows us that, for example, if we start with a strong negative field, to set it up in one of the antiferromagnetic states. And if we set it up from the other side, we get it back in the other antiferromagnetic state. Well, so we know we can in principle set it in one of the antiferromagnetic state by wish in the system, but we eventually can't distinguish by our linear response. So now if we look to the nonlinear response, to the second order magnetoresistance, this resistance is dependent on the perturbation I use with my current. So I perturbate my system with this current. And if this perturbation, well, which is in our case the spin orbit torque, which is generated by the spin Hall effect in the two layers, by the spin accumulation at these interfaces, which then gives a torque to the magnetization, right? And as you can see, this spin orbit torque changes direction when the magnetization for one antiferromagnetic state or for the other antiferromagnetic state. So it should be, in principle, allow us to measure our signal. Unfortunately, another requirement we have here, that the linear response magnetoresistance as a function of this perturbation should be not at a maximum or at a minimum, right? So the differential of this magnetoresistance should be not zero. And indeed, this is not the case in an out-of-plane anisotropic material. However, if you apply a small perturbation with a magnetic field, if you perturbate a little bit your system, you actually will change this and you should be able to measure this nonlinear AMR. And indeed, as I show you here, applying now a saturating field where you come from a negative side or from a positive side, where we know we can in principle polarize our antiferromagnetic state at zero field, we then can, by a small in-plane magnetic field, which perturbates our system just a little bit, we can nicely distinguish at the second order magnetoresistance, which is measured here, the two states. And it changes the sign if our DC perturbation due to an applied magnetic field, the in-plane magnetic field, has changed. So yes, we can actually we can distinguish our two antiferromagnetic states simply by a transport measurement. And if we compare now this, if we first of all try to understand what is generating this possibility of generating this nonlinear magnetoresponse, we figure out it's the anti-damping spin-orbit field, which has a staggered nature in our system. Well, it's not only the second order magnetoresistance, which is generated by the anti-damping spin-orbit torque, but it's also the switching possible again. So we can actually switch our antiferromagnetic system by current pulses. And here we apply again a little trick. We have normally the energy barrier, which corresponds to the anisotropy energy barrier, which is quite high, which actually makes, one of those states has to overcome this energy barrier to flip in the other minimum. And this energy barrier is extremely high, such high that thermal fluctuation are far not enough to do this at room temperature. So normally those systems are absolutely stable and they will stay in one of those states. But when applying a small in-plane field, effectively you start now counting your antiferromagnetic states. Still they are distinguishable. Well, the first layer has this, the first arrangement is like this, the other arrangement is like this. Yeah, and the energy barrier is reduced. Now, applying in principle a current will allow us to switch between the two states. And this I will show you in the next slides. Okay, here we have our anomalous Hall effect measurement, which can distinguish the two ferromagnetic states when we apply a strong enough field. And we know because of this hysteresis, we can set up it in a particular state. And this particular state, when measuring now our second order response, corresponds to this value. Yeah, and we can apply a pulse in this positive direction. And what we will figure out, nothing has changed. We measure our second harmonic signal as a function of this perturbating field very nicely as expected. Well, if we apply the signal from the other side, our response has changed corresponding to the opposite state. So indeed, applying now two pulses will change between those two states, right? We can also start from the other side and we will find the same thing. We can change between pulses from one side or pulses from the opposite side, our antiferromagnetic order, and we can read it out in this nonlinear state. If we compare it with a fully polarized state, which we have generated by totally polarizing the system in a ferromagnetic state, we see that the signal which we measure is the same than the signal which we have generated by our electrical pulses. This means these pulses at this particular current densities enable us to fully polarize our antiferromagnetic state. Now, what happens if we do it in a more careful way? So if we use a strong pulse, say a negative pulse, to reset our system in one of the antiferromagnetic states, and then we apply a much smaller writing pulse and the even smaller reading pulse, right? And we do this 10 times to have some statistics. And this we do for different writing pulses of different magnitude. Right? Always 10 times to get a little bit of statistics. What you will find is that you actually see in your second harmonics measurements that you actually not generate just the fully polarized states, but you can actually generate a lot of intermediate states. Yeah, we are back to our memristor, our system, which can act like a counter, where we can have not only 1 or 0, but we have an analog memory, if you want. And if you just look to the statistics we did, the measurement uncertainty is actually much larger than actually the uncertainty just from doing 10 measurements. So we always, after polarizing the full system using the same kind of pulse, we switch exactly in the same intermediate state. So it's an extremely reproducible system. Interestingly, our normal linear response, first harmonics, doesn't change at all. And this at a scale of our normal response, if we go from a parallel to anti-parallel state, which is 3 orders of magnitude more sensitive, right? So the first harmonics doesn't tell us anything about it, but the second harmonic tells us what state we are and what intermediate state we are. How is it possible to have those intermediate states? And the thing is, well, before I come to this, I show you that these intermediate states have an extremely long retention time. They're actually non-volatile, at least from the time we measured them, they don't change. So you can set them up, you can switch between them. First of all, we do a kind of reference measurement, switching in 2 extreme polarized states, single polarized state, single domain states, and then we switch in the intermediate state. This is done by a reduced barrier height. Then we switch off our in-plane magnetic field. We go drinking a coffee, waiting an hour, and starting measuring it again at a reduced barrier height. And what we will find is exactly the same state, having survived for 1 hour in this case. And as a reference, again, we switch to the 2 fully polarized states. So yes, you can have in principle a non-volatile memristor type of device. And well, what is the origin of this? Why those guys are staying that long? And if you look with MFM, because it's indeed a synthetic antiferromagnet, you can do the same experiment. You set it up into intermediate state, and what you will find is domains and domain walls, right? You see domain structures in your stripe of a very small dimension, which remain unaffected by magnetic field because these are antiferromagnetic domains, right? And if you just count the area which has reversed and divided by the area which hasn't reversed, so it's just shown here in green and blue colors, you will find exactly this ratio will give you exactly the signal what you are measuring. So indeed, this partly reversed domain structure is the origin of our memristor structure. So this is quite interesting. So this is a synthetic antiferromagnet. This is something, well, it's not really an antiferromagnet. There's only 2 ferromagnetic layers which are antiferromagnetically coupled via RKKY interaction. Let's go back to our copper manganese arsenide with our broken T and P symmetry and combined PT symmetry. And we do the same experiment. We send the current to switch the Néel vector in one direction. We send the current to switch the Néel vector in the opposite direction. And we do it many times. And as you can see, our second harmonic signal gives us exactly what we would expect, 2 opposite values. And now we wait not only for 1 hour, but for a whole day. And those states are absolutely robust. Again, the origin of this are domain walls, antiferromagnetic domain walls, now measured in this copper manganese arsenide and PMXMLD measurements. For this, you need actually a huge synchrotron equipment to be able to have enough energy to measure those the XMLD signal of these antiferromagnetic domain states. Yeah. Well, what we did was to so you have 2 antiferromagnetic domains and the domain wall between. And what we did is we developed actually a new method, which is based also on magnetotransport, but in the thermal regime, where we use a near-field scattering microscope. Yeah, and we did this near-field anisotropy, where you shine a laser light on this metallized tip, and you use the stray field, which is generated, the near field, not stray field, sorry, the near field, which generates locally a small heat gradient of very small dimension. And what you measure globally is the electric response. And here you see the AFM picture of this measurement. It's just a stripe of 2 micrometer wide, has no structure. But if you look to your thermal voltage, which you generate by this method, you can see actually a lot of like spaghettis here, all these black lines, and actually they correspond to domains. And when you analyze the signal and to understand this thermal this thermal current you generate and what is the response to this, then you will see that each antiferromagnetic domain has to change its sign. So what is blue and red are actually antiferromagnetic domains in this stripe, measured by this relatively simple method compared to a pin measurement. And what we now did is exactly we applied a current pulse and see what happens to this domain structure, which we can then measure in situ. Yeah, and this is what happens. So if we apply a current in one direction, the red domains shrink on the expense of the blue domains, and if you send the current back in the opposite direction, now the blue domain shrinks on expense of the red one. So you can actually repeat this experiment very reproducibly, and you will get always back to the same domain structure after the pulses. So also in real antiferromagnet, like our model system, the synthetic antiferromagnet, the same principles actually apply. Okay, so by this I want to finish now my talk. My question is, do you think it's possible to do spintronics with antiferromagnets? And I hope I have answered this a little bit towards yes, because what we've shown in the synthetic antiferromagnet with PT symmetry is that indeed you can switch your Néel vector by 180 degrees using spin orbit torque driven domain wall motion, and you detect it with this spin orbit driven, if you want, was generated nonlinear magnetoresponse. And you can do even better. You can actually apply smaller intensity current pulses, and you can only generate multi-domain states, and they are non-volatile, right? This we have shown as well. So we're creating a memristor type of device, maybe really interesting for application. And in the real antiferromagnetic copper manganese arsenide, which also has a Néel temperature well above the room temperature, all these measurements I shown you were done at room temperature. There's also this PT symmetry, behaves the same way. You can also electrically switch the Néel vector by 180 degrees, and you can detect it with this spin orbit driven nonlinear magnetoresponse. And yes, this is more or less what I wanted to show you. And thank you very much for your attention.
Yeah, thank you so much, for this wonderful talk. I'm really sorry again for this confusion regarding the Zoom license. On behalf of everyone, I'd like to thank you. So we have still 15 minutes roughly in this session. So we can take some questions. So I would request the participants to either raise hands or type in the chat box if you have some questions. Maybe I can begin with, I have several questions, but I can start with your domain walls. So in the bulk antiferromagnet, that's the copper manganese arsenide, you have seen this kind of string-like behavior, and I understand it's fine. It's the XMLD, so you are more sensitive to the walls. But for the MFM images, when you saw, so there were like string-like features. So are these like 360-degree domain walls, or what it is?
So what you see here, right?
Yeah.
So clearly, first of all, you can distinguish the domains.
Yeah.
Because it's not really an antiferromagnet, it's actually a synthetic antiferromagnet, and those two layers are not fully identical.
Yeah.
So there is a stray field which you can detect, and which is then possible to identify MFM. And similarly, your domains here, the domain walls, are visible now as a kind of double contrast, white and black. Yeah, and this is actually due to the stray field coming out from the two layers, from the two antiferromagnetic layers at the boundaries. You not even need a domain wall. This is entirely due to the stray field generated at the point where the magnetization diverges, right? And this stray field is coming out at the position of a domain wall, or coming in at the other side of the domain wall. That's why you see this black-white contrast here. That's the origin of it.
Okay, but then I wonder, let's say if you take the image of just one layer, like you will use a technique which is just surface sensitive, and you are sensitive to the top ferromagnet. Would you expect similar structure, or you will expect a different structure?
Yeah, like definitely. Yeah. This will be those antiferromagnetic domain walls here are they're the boundaries of domains on the upper and the lower layer. Yeah.
Okay.
Because the interaction, the RKKY interaction, is quite strong. It's of the order of half a Tesla to a Tesla. So we use iridium here, and this has a relatively large exchange interaction. So it would not be possible that you have parts where the upper layer and the lower layer are ferromagnetic, and parts where they are antiferromagnetic. The exchange coupling will always make it antiferromagnetic. Even the domain walls, they will be in an antiferromagnetic state. They might be slightly charged in the sense that because we have this magnetic stray field coming out from those layers at the point where the divergence is non-zero. And this stray field may count slightly the magnetic orientations of the upper and the lower layer at the domain wall position. So the domain wall is not perfectly antiferromagnetic. So it maybe has a little twist towards the direction of say it's a bit like it's a little bit effect of like the Sylodzinsky-Moria interaction. You get a bit of kind of charged domain walls here. Yeah. But in principle, those the structure all over the place is fully antiferromagnetically coupled. Yeah.
Okay, thank you. So that means they are kind of 180-degree domain walls.
Yes, these are 180-degree domain walls. That's why also 180-degree switching. Yes.
Yeah. I mean, why I asked that question, because in the next slide, when you saw the thermoelectric images, you see these strings-like features, not for the copper manganese arsenide, for the synthetic antiferromagnet. Somewhere, I think.
You mean before?
I forgot. Somewhere you saw this string-like.
You mean the P measurements from the?
I think it was towards end.
It was very in the beginning, I guess. Maybe.
No, it was towards the end.
Okay. You mean those?
No, you go next. I think here.
Yeah.
The thermovoltage magnitude, you see this string-like feature. So they are basically coming out of the uncompensation between the two ferromagnetic domain structure.
Because actually the origin of this is this thermal voltage generated because of the magnetosiebeck effect.
Okay.
So now you have, this is in principle the thermal equivalent to the AMR.
Okay.
So at those boundaries, right, if you come with your rotational symmetric heat gradient, right, you will not generate any signal if you are far away from such a boundary. And if you're exactly on such a boundary, also, you will not generate any signal. But if you come towards this boundary, then you will generate a signal.
Okay.
And so each boundary will be actually, depending from which side are you coming. So you get, for example, a negative signal or a positive signal. The magnetosiebeck effect is equal in the two domains, despite they are 180 degree, because they are 180 degree rotated. But at the place where the domain wall rotates, here the magnetosiebeck effect is different. And this difference, the differential between the magnetosiebeck effects in the domain and at the domain wall is actually what you see here. This is the interpretation of this of those measurements.
Yeah. So well,
and when we, for example, switch with a current, and we send the current only. This is only a bar device, right? We can send a current from up to down, or from down to up, right? Depending now on this current direction, we enlarge one of the domains on the expense of the other, or we reduce, right? This was, yeah. So you can see, depending on the current direction, you make it larger or smaller. And here it's if it would be a 90-degree domain wall, you would may move them, but in a totally different way. They would not reduce or enhance. they would just maybe shift parallel or something like this. But here it's really like a Zeeman field acting on a ferromagnetic domains. They either enlarge these domains or they reduce the domains. It's very similar.
Yeah. I mean, thank you very much. Well, there is a student, very undergraduate student. I'm teaching them. So I think he's asking about time reversal symmetry. Rishi, I have to tell you, this is more fundamental. You will learn this. So when you go to the introductory condensed matter physics, I think we can skip it. For these are the origin for ferromagnets, ferroelectrics, time reversal symmetry, inversion symmetry, and all. I will talk
maybe
about.
one can see it like if you reverse the time. So, well, if you have a magnetic moment, you can consider it being generated by a current, right? And if the time reverses, a current runs the opposite way, right? So you have a current path, circular current, which generates your magnetic moment pointing, say, towards my right thumb. And if the current runs the opposite direction, because the time has reversed, then your magnetic moment has changed orientation. And so if you have a system where your magnetization, which is magnetic, at the moment where you switch the magnetization, this corresponds like the time would now run the other way around, right? This is what is meant with time reversal braking.
Okay, thanks. Thank you so much for explaining nicely. Are there questions from others? Kindly raise hand or ask on mute. Yeah, Akilan, go ahead.
Sir, great talk, sir. Thank you. Sir, I would like to know if intermediate states in the Hall resistance is possible in common bilayers of heavy metal and ferromagnets, which have perpendicular anisotropy.
Sorry, can you repeat your question? I did not. You asked me about the anomalous Hall effect in bilayer system?
Yes, sir. Yes, sir. Can we achieve intermediate states in the Hall resistance in normal heavy metal and ferromagnet heterostructures?
Yes, normally yes, and it's typically quite strong because the anomalous Hall effect at the interface gives you usually the largest contribution, because the anomalous Hall effect is also due to spin-orbit coupling. Yeah, I think there are various origins of the anomalous Hall effect, but the one of the quantity where it scales with is the spin-orbit interaction. If you have a heavy metal, usually you have a strong spin-orbit coupling, and these hybridized states at the interface, which are both magnetic and also having a strong spin-orbit coupling, they generate you a large anomalous Hall effect. So yes.
Yes.
Thanks, Akilan.
Yes, thank you.
Questions by any others? Kindly feel free. We still have a few minutes. Not really. Okay, I think, I mean, we saw, I just wonder one more thing. I mean, there is few minutes left. I'm really excited to see how the second harmonic magnetoresistance actually is helping to see the switching. Let's say you have a multi-layer of, synthetic antiferromagnet. You have taken a simple, like ferromagnetic 1 and ferromagnetic 2 separated by some spacer. But if you repeat the stack, we can also see intermediate steps, switching. If you measure, let's say, hysteresis and so on. Could you sense that also in this technique? I'm just curious.
So you say if you have not only two ferromagnetic layers, but you have a couple of antiferromagnetically coupled ferromagnetic layers.
Exactly.
They may switch. Well, I think at zero field, if your exchange is strong, you will have always antiferromagnetic coupling. If you, on the other hand, make a sweep by applying a magnetic field, then you may see, I mean, here you see it for only two layers. You get this small hysteresis, right? Oops. So here, for example, we're measuring the anomalous Hall effect. You see the small hysteresis. And since these layers are not fully identical in a synthetic antiferromagnet. Here you see also a little, you see this hysteresis. And if you have more than only 2 layers, you get inner hysteresis loops and outer hysteresis loops as well. So here you can actually see it already in the first harmonics. And the second harmonics, as I said, this gives you information about the perturbation due to the spin orbit field. So when you are, when you think about, you have a certain configuration of your multi-layer system, and then because of interfacial effects or of spin Hall effect, spin accumulation at interfaces occur, and then torque your magnetic order in a certain way, this will be then correspondingly the response. And the response can be in principle originating from the anomalous Hall effect, yeah, or it can also originate from an anisotropic magnetoresistance effect, or even from a giant magnetoresistance effect if there is some spin transport, some spin conserving transport through such an interface like a GMR, right? So yes, you will see probably a very complex second harmonic signal, which could give you additional information about what of the layers is in which direction. Yes, I think it could be quite interesting. So we haven't done those experiments yet, but it's, I think, something which one could try and try to compare maybe these hysteresis loops we have anyway in a normal linear response in those higher responses. When measuring it at you bias it with an AC current and you look into your second harmonics, for example, right? Yes.
Yeah, I mean, that would be very interesting. I mean, I can discuss that probably later more in depth with you, because we are working on similar systems. And I'm just curious if this can provide, you know,
could provide, I guess, definitely more information, because here, even in this simple system, it already provides you information about something. The normal linear response doesn't tell you anything, right? When we compared those measurements here, the linear response remains absolutely constant when having all these intermediate states here. Yeah.
Yes, thank you so much. Great. Maybe we can take a very last question if there is any. Otherwise, we can present the memento to Joerg. I think there are no more questions. So, Puspendra, could you kindly share the memento on the screen? So, on behalf of the W2S team, I like to present this very small digital memento to you.
Thank you very much.
Yes, I will read it for you on behalf of everyone. So, W2S seminar webinar series on spintronics, National Institute of Science Education and Research. That's our institute, NISER, Bhubaneswar in India. Takes pleasure in presenting this plaque to Professor Joerg Wunderlich from University of Regensburg in Germany, in recognition and appreciation for being a valuable speaker to give a lecture on spin orbit torque, switching between reversed antiferromagnetic state and its electrical detection. Thank you so much, Joerg.
Thank you very much.